Hey everybody, in this video I'm going to talk about domains of functions. We're going to use some fairly simple ones so we can get the point across. They can get more complicated, and if they do and you find one that you don't think I've fully explained, please contact me or mention it during one of our face-to-face meetings in Zoom. Alright, so the very first thing you want to think about with domains is, people get really wrapped up with this. The best thing to think about with domains, the best way to think of it is, remember, because domain is input, what goes into the function, you start to ask yourself the question, what's allowed to go into the function? And the best way to think of it is everything and look for exceptions, right? And I got a couple of pretty simple examples to start with here. So we'll start looking at x squared, saying, what am I allowed to square? What numbers can I square? Well, you can square any positive number, like 5 squared is 25, and so on. 0 squared 0, because 0 times 0 is 0. Negative 1 squared is positive 1. Negative 2 squared is positive 4. You can square all the negatives. You can square every fraction. 1/2 squared is 1/4, and so on. There's no numbers you can't square. And if you were looking at this graphically, it's a parabola, right? This is a parabola. So we could look at it in Desmos. This is the graph of x squared. And as you can see, if you're looking horizontally along the x-axis, it covers every value for x that there is. I don't care how big you make it, it still exists out there. I'm going to zoom back in. So one way to look is graphically. And how would we write this? Well, we want to put negative infinity to positive infinity using our interval notation. You could put all real numbers. Notice I didn't include either one of those. Now here's a different guy altogether here. We start talking about square roots, we might have a little bit of a different issue, because there are numbers that I cannot take the square root of. If you think about that, if you start looking at positives, you're not going to have any trouble. Square root of 4, 2, 9, 3, and so on. But if we went down towards 0, well, you can take the square root of 0, because 0 squared is 0. But if you go to the negatives, you got issues, right? Because we all remember Math 2, you learned that there are complex solutions to subquadratics. So if you look at, say, what's the square root of negative 1? Well, that's the definition of what I is. I is the square root of negative 1. So that's not, the output's not real. So if we have negative input into this function, the output is a non-real, that can't go in the domain. Okay, so that's a domain restriction. So the domain of this one is everything that's negative. So I want to show you this one, and I'll show you on the calculator, I guess. One way to look at it is graphically. So just talking here, we say that it's 0 to infinity, right? So anything 0 is okay, and everything positive is okay. And we would write it. Let's go ahead and write it, and we'll go look at it on the graph too, just to nail this thing down. So we're allowed to put in 0, and that's the farthest thing to the left with our interval notation, and we'll go to positive infinity, and we can't include that because I don't know what number it is. Okay, so there's how that would look. Now graphically, how would we see it? I've already got it in here, but let me, there we go, turn it on, turn this one right here off, and let's refresh this graph. All right, so look over here, and you can see it starts at 0. Now remember, we're looking horizontally or along the x-axis. It starts at 0 and goes to positive infinity. And that's one way to see it graphically. Okay? All right, so what's another thing we could write here? One thing that's important to realize this too. Now this comes up when we start doing something called piecewise functions. The domain of x squared is all real numbers, but domains can be stated explicitly. That means they're giving you a domain restriction explicitly. They're saying, hey, I know it's x squared, normally all real numbers, but I'm only allowing it to live from 0 to 5, not including either one. That's what this means. Interval notation, we could say that, we could write it, but I'm not going to get into that. I want to show you how to graph this in Desmos. That's a good way to do these. And so I said, what's the graph of this thing look like? Well, it's x squared. Now to put a domain restriction into Desmos, and you need to memorize this, and you're going to get plenty of practice, squiggly bracket, I don't know the real name for that thing, brace, I guess, less than x, and just put that inequality right in, just like you just saw it, and it will graph the piece where it's allowed to be. So this thing's only allowed to exist for values from 0 to 5. and that's where it's at. Okay, so that's how you enter a piece of a function in, or one within a restricted domain. Okay, move. Oh, I didn't mean to do that. Not the whole thing. All right, moving on here, we're going to go back to the notes, and we're going to get other domains here. All right, they could get more complicated. You get the square root of x plus 5. Now, yes, you could graph this. That's true. They can get, but I'm going to show you how to do it by hand in case you get one that's a little more complicated, like say this one down here. Now, again, we're dealing with square roots, and the rule of thumb goes like this. Does it have a domain restriction? If it's a polynomial, that's what this is. It's a quadratic. It's always all real numbers, unless otherwise stated explicitly or restricted by context. Like if it was a ball, a path of a ball, or something like that, and and it was a function of time, you wouldn't have negative time. Things like that do restrict them, but in the generic sense, it's all real numbers. Okay, so now we're looking at a square root function here, and we know there's issues with negatives, and you might can guess and check your way and say, well, I could put in a -1 plus 5 is 4, and that works, and work your way down. You can look at it graphically, but a quick way to do these, I just want to show you the way to work this out pretty quick by hand, is solve an inequality. You take whatever's inside that square root, and you write it this statement. You say, well, this, whatever it is, I'm using a simple one, this is a matter of fact. It's got to be greater than or equal to 0. And you solve that inequality, and that will give you your domain. So your domain is x is greater than or equal to -5. Right? So that's what we would put in our interval notation. X is greater than or equal to -5, which we would write bracket. Oh, here I go with my squiggly bracket. -5 to positive infinity. Right? And that's how that would look. All right, let me do this next one. If I have time in this video, I'll come back and look at the graph. I urge you to graph that and make sense of that domain yourself. Or you can look at it as shifted left 5 units. That's another way to look at it. All right, so now if you're dealing with, so anything radical is going to give you issues, especially even roots. Well, I guess specifically even roots, you're going to have domain issues. All right, and if you have a variable in the denominator, you've got issues. Not always, because it can be tricky where it doesn't have a 0 coming out. Anything that makes this denominator 0 is a problem. So to solve that one, you take the denominator, which is 3x minus 6. Oh, that's not what I wanted. I wanted that. I want to minimize that. All right, so let's clear this out and work that out. 3x, is it 3x minus 6 or plus 6? 3x minus 6. So we're going to solve this simple equation. Where is 3x minus 6 equal to 0? Remember, it can't be 0 this time. And we'd add 6 to both sides, and we'd get that, right? And dividing, we find that it's 2. In other words, ours says, hey, x equals 2 makes this 0. So that means x cannot be 2, right? Because 2 causes a problem for our denominator. And that's how we would look at this one. So a way to write that, honestly, in interval notation is more complicated. A good way to write this one would be the old way, where you would use, remember doing this, x, and then you would put in such that x, and then you would go up here and get this symbol. Where's the not equal? Seems like it's an important one to have. Oh, there it is. Not equal to 2. Can you see that on the graph? Probably not. Oh, it'll be a vertical asymptote, actually. Yeah, you would see it. Interval notation, it would look like this. You would say, boy, it'd be a lot of work. It'd be negative infinity to 2 union 2 to infinity. So it would be a little bit more complicated. So I don't have time to type that in this video. Let me just draw it out for you. If it couldn't be 2 and you were doing interval notation, you would write it like this. You would say negative infinity to 2, can't include it, and then 2 to infinity. So the only number you're leaving out is that 2. And I think that's more cumbersome than the set notation piece. But anyway, that's it for this video. I hope this is helpful for you. I know it's a little bit long, but if these examples aren't enough, get in touch with me, and I'll look at it specifically on the assignment with you. Okay? Thanks for watching.